Okay, so average rate of change is something you've seen before, and given this formula, the change in y over the change in x, well, f of x2 minus f of x1, that's y2 minus y1, right? This is the slope formula. And it's the slope of a line. Well, if I give you a curve instead of a line, then the average rate of change, it averages how it's changing from one point to the other. I don't know exactly what the slope of a curve is, but I can say it's an average. So, you know, if I draw some curve, and I want to know how it's changing from x1 to x2, by calculating the slope of the line that connects those 2 points, that's not a very good job, but by calculating that, I at least have some information about how the curve's changing. I know if it's increasing, I know if it's decreasing. Overall, it could have lots of bumps and changes in between, but overall, I have a general idea about it. Okay? When we have, and let me do a little bit better job of drawing that. When we have a line that crosses through, it's still not a very good drawing, that crosses through a curve at 2 points, we call that a secant line. Okay, you probably learned that in geometry and then very quickly forgot it. And it had to do with circles at the time. A line that crosses through a circle in 2 points is a secant line. A line that touches a circle at 1 point is a tangent line. Well, we use the same terminology for curves in general. Okay, now if instead of saying it's the distance between x1 and x2, I say that x2 is x1 plus some distance h, I can get a more generic formula here. And this is going to lead us eventually to finding slopes of tangent lines instead of average rates of change, which are secant lines. So when I do that, notice that my denominator simplifies because my x2 is x1 plus h minus x1, and that all simplifies for my denominator to just be h. Okay, so let's use these formulas to do an example. I have free fall motion. The motion of my object, or my rock in this case, is defined by y equals 16 t squared feet. Okay, so that y is the height of my object after t seconds. What is its average speed during the first 2 seconds of fall? So what they're asking me to find is over the interval from t equals 0 to t equals 2. Okay, so now I'm using t's instead of x1 and x2, but it's going to be the same formula. So this is going to be my t1, this is going to be my t2. My f of t1, I evaluate the function at 0. Well, if we plug in a 0 for t, we get 0. And my f of t2, we're going to plug in a 2, so I've got 16 times 2 squared. That's 16 times 4. And what is 16 times 4? 32, 64. So my average rate of change, my change in y over, in this case, my change in t, is going to be my f of t2, which is 64, minus my f of t1, which is 0, over t2 minus t1. So I get 62 over 2 is 32. Now my y is defining the height in feet. My t is in seconds, so the units of this would be 32 feet per second. Okay, let's try it between 1 and 2 seconds. So I've got the interval now going from 1 to 2. So my T1 is going to be 1, my T2 is 2. We already evaluated f of T2, that's 64, but I need f of T1, so that's my function evaluated at 1, and we get 16. So my change in y over my change in t, which is my average rate of change, is 64 minus 16 over 2 minus 1. I'm just plugging into that formula from the previous slide, and I get 48 feet per second. Okay. What is the instantaneous speed at t equals 1 second? So they didn't give me an interval of x values. If it's just at t equals 1 second, then my t1 equals my t2. That means I'm going to be dividing by 0. Right? If we go back to this formula right here, if my x2 equals my x1, I'm dividing by 0. That's no good. But that's how I'm going to get to the instantaneous speed. So what I'm going to do is I'm going to define my delta t generically. I'm going to say my delta t is going from t naught, that's the initial t value, to t naught plus h. Then if I want to find my average rate of change, my change in y over my change in t is going to be, now remember we're using the formula y equals 16t squared, would be 16 times t naught plus h squared, because that's my t2, minus 16 times t naught squared over h. Okay, now, we're letting our t naught be 1. That's the time that we're interested in. So I'm going to replace those t naughts by 1. This will become 16 times 1 plus h squared minus 16 times 1 squared would just be 16 all over h. All right, well, I got to multiply this out. What you're going to find is that stuff is going to simplify once I clean this up. So I'm going to multiply 1 plus h times 1 plus h. I'm going to FOIL that out because that's what 1 plus h quantity squared is. Okay, so my first gives me 1, outer gives me h, inner gives me another h, last gives me h squared. So this thing becomes 16 times 1 plus 2h plus h squared minus 16 all over h. Okay, well then I'm going to distribute that 16, and I get 16 plus 2h plus h squared minus 16 all over h. Well, 16 minus 16, that goes to 0. And what I'm going to be left with, every term has an h in it. So in the numerator, I can factor out an h, and that'll leave me with 2 plus h. Oh, I made a mistake. Hold on. I didn't distribute my 16 completely. Look at that, y'all. So this changes. I have 16 plus 32h plus 16h squared minus 16 over h. 16s go to 0. And I'm still going to factor out an h. There's an h in everything here. So if I pull out an h, I'm left with 32 plus 16h. And that's all over h. So the h over h will go to 1. Okay, so what this tells me, whoops, I need a new slide. Let's come back up here. Is that my average rate of change in general is 32 plus 16h. Now remember what h is. H is the distance between my t1 and my t2. But if we are at the instant of t equals 1 second, that means we want h equal to 0, right? We calculated this as if t1 was 1 and t2 was 1 plus h. But we don't want h to be anything. We want to know exactly what's happening at t equals 1. So if h is 0, then we're going to get the average rate of change, or sorry, I take that back, the instantaneous speed at t equals 1 second is equal to 32 feet per second. Okay, so in the example we just did, which was more specific, we actually found the slope of the tangent line, and we got to it. We didn't take a limit. It's just at the very end of the problem, I said, okay, but we want h to be 0, so let's substitute in h equals 0. Well, what do we do when we find a limit? We do a direct substitution, right? So we actually did this. All right, so we're going to do one now. Find the slope of the curve, y equals 1 over x, at any point A. Okay, so we're being generic again. As long as A doesn't equal 0, because, then we'd plug in 0 and we get 1 over 0. We can't do that. 0 is not in the domain of this function. Once we find for any point, so we're going to get an answer for the slope in terms of A, we're going to check and see what it is when A equals -1. Okay, so that means the interval that I'm doing, I'm looking for what's happening at A. My second point would be A plus h. And then at the end, as we let h go to 0, the h will go away. All right, so my f of A is going to be 1 over A. I'm just plugging in to my function. My f of A plus h is 1 over A plus h. So a minute ago, I told you that that formula might remind you of something called a difference quotient. A difference quotient is this part of the formula. The numerator is a difference, and then we're dividing by something. Dividing is a quotient. Okay? So that part right there, I call it the difference quotient. I abbreviate it DQ. So before I worry about doing any limits, I'm going to find the difference quotient. When we do these, the difference quotient is always going to get, let me go back again, the h out of the denominator. Because if the h stays in the denominator, when I do the direct substitution, I'm going to be dividing by 0. So when these are done correctly, that h in the denominator should simplify with something in the numerator. Okay, so my difference quotient, we're going to plug in here. It's my f of A plus h, which is 1 over A plus h, minus my f of A, all over h. Okay, so what I did there is I plugged into this difference quotient formula where my x naught was a. All right, now, this is why we did limits analytically. We know how to simplify this and clean it up, right? What do I need to do? Common denominator. So what am I going to multiply top and bottom by? A times A plus H. All right, so that's going to get rid of my denominators that are in my numerator when I distribute this whole thing to both of those. When I distribute it to the first fraction, the A plus H cancels, and we're going to get A. For the second fraction, the A's cancel, and I get minus the quantity A plus H. The denominator, we just write it out. We don't distribute, we don't do anything to it, because that H, we want it to cancel. Okay, so if I distribute this negative here, my numerator is A minus A plus H over H times A plus H. And A minus A goes to 0. Do you see now I've got H over H? Yes, thank you. Yet another reason I am not going to post this. Good catch, y'all. Okay, and that is going to simplify to negative 1. So I get negative 1 over A times A plus H. All right, so all of that is called the simplified difference quotient. To find the actual equation, the slope of the tangent line, we have to take that and take the limit as h goes to 0 of it. Okay, direct substitution gives me negative 1 over a squared.
So you're going to do the limit of the difference quotient?
Yes. Okay, so we found the slope of the curve at any point A, because now it's in terms of A, but they asked us, what is the slope when A equals negative 1? Okay, fine. My slope when A equals negative 1 would be negative 1 over negative 1 squared is negative 1. Okay, so everything we've been building to in this class is to be able to find the slope of a tangent line. And not necessarily a tangent line, it's a tangent line to a curve anywhere on that curve. So basically, the slope of the curve, as opposed to an average rated change of the curve, we're going to find slopes of the curve. Okay, now these have meaning in real life applications. And we're not going to call it slope every time I ask you to find it. What we just found is a derivative at a point. So in the future, and I'm going to ask you probably every day, if not multiple times a day, how do you find slope? And your response is, find the derivative. Okay, those two are interchangeable. A lot of times I'm just going to ask you to find a derivative. Most of the time I'm going to ask you to find a derivative. And then every once in a while I'm going to go, what's the slope at this point? And then I'm going to say, how do you find the slope? And y'all are going to tell me, find the derivative. Okay, so I just kind of wrote it on the other slide. But officially, the formula for the derivative of a point, right there. But I just wrote it on the other slide, so if you just added it to your formula before, you don't have to write it again. Okay, so the derivative is telling me how my curve is changing at that point. What's happening to the left and the right of it? Is it increasing? Is it decreasing? It gives me a general idea. Okay, now if I know the slope of the curve at that point, I can write an equation of the tangent line. And the way you were taught to write equations of lines was point-slope form. You need the formula y minus y1 equals m times x minus x1. All right, well, the way they gave me this problem, they want to find the equation of the tangent line to the curve at 8, 3. Well, right there, they just gave me my x1, y1. So to write the equation of the line, the thing I'm missing is m. M is slope. How do I find slope? We use that derivative formula. All right, so the first thing I'm going to do is find the difference quotient, right? I want to do that first, get the algebra out of the way, then we'll take the limit as h goes to 0. So I need what do I need? Hold on. I am going from 8 to 8 plus h. Ooh. I had a brain fart for a minute. So my f of 8 is the square root of 9, right? Because I plugged 8 in here. 8 plus 1 is 9. Square root of 9 is 3. And then my f of 8 plus h is 8 plus h plus 1. So I get the square root of 9 plus h. So for my difference quotient, I get my f of 8 plus h, so that's the square root of 9 plus h, minus 3 over h. All right. We got square roots in this problem. How do I simplify the difference quotient? I'm going to multiply by the conjugate. So the conjugate is going to be the square root of 9 plus h plus 3 over the square root of 9 plus h plus 3. In the numerator, we FOIL that out. And we're going to get the square root times the square root gives me 9 plus h. Middle and outer terms cancel, that's why we do it. And the last gives me minus 9. That's all over h times square root of 9 plus h plus 3. So 9 minus 9 goes to 0. And h over h goes to 1. So my simplified difference quotient is 1 over square root of 9 plus h plus 3. All right, so our derivative at 8, or our slope m, is the limit as h goes to 0. Make some room here. Of our simplified difference quotient. And when we do a direct substitution, we plug in 0 for h. I get 1 over the square root of 9. Well, that's 3. Plus 3 is 1/6. Okay, so that is the m that I'm going to plug in right there. Okay, so equation of my tangent line. Y minus y1, I get from up here, it's 3, equals 1/6 times x minus my x1 up here is 8. And if I'm giving you a test, I'm good with you stopping right there. That is a perfectly good equation of a line. If you keep going, you're likely to make an arithmetic mistake. So for me, on a test, on a quiz, stop. If it's multiple choice, you probably have to keep going. In my math lab, you're going to keep going because they're going to ask you for y equals what. So if we have to keep going, we distribute the 1/6. I get y minus 3 equals 1/6 x minus 8/6 would be 4/3. Then we add 3 to both sides. So I get y equals 1/6 x minus 4/3. 3 would be the same thing as plus 9/3. So final answer, 1/6 x plus 5/3.